So this week we're going to add a new mapping skill that's going to require you to be able to determine the elevation of a feature based on lines on a map or on a topographic map. These are called contour lines. And this skill is really useful in helping to identify different types of land features, to make predictions about where things could erode, looking for oversteep banks, looking for erosion, and several other types of applications. So basically what we're looking at is the three-dimensional piece of the landscape. So we've talked about the XY locations, or actually YX locations, because we're talking about latitude and longitude. And then the third element would be the Z. X, Y, and Z would be the elevation. And so we can look at and Google Earth and see it in 2-dimension, but you can also look at the profile of an area. So this is kind of the way it would look if you could slice something in half and see that elevation. So contour lines or elevations on a topographic map can be shown in many different ways. You can have what's called a benchmark, or a BM, that is indicated by an X on the map. And so, for example, this is a benchmark and it's 241. And you might say 241 what? Usually on a map it will tell you what the elevation dimensions are, whether it's feet, kilometers, whatever. So this is in feet, so 241 feet. You can also have something just called a spot elevation. So for example, this 220 with the X is a spot elevation. So that's one way just to get random elevation on a map. A more conventional way or systematic way is by what are called contour lines or ISOLINES. An ISOLINE is kind of a dot-to-dot game where the line connects the dots that have some continuous value. So with the maps that we're going to be looking at, we're talking about continuous elevation value. But you see these on weather maps all the time. There'll be an isobar showing lines of equal pressure. Temperature would be an isotherm, or seafloor depth would be an isobath. So contour lines are created by extrapolating or connecting the dots between elevation points. So you might, back in the day, have surveyors go out with their stadia rods and identify points that had a certain elevation, and then they would kind of connect the dots to make these continuous lines of elevation. The idea being that if I were to walk, this is probably an island because this lower contour line is 0, so it's at sea level all the way around this circle. And then as I move to the next line, that's indicated as 10. The bottom of this little image, it says contour interval is 10 feet. So every time I cross a line, I have theoretically moved up another 10 feet in elevation, and theoretically, if I were to walk along that imaginary line on the landscape, I would not be changing my elevation. I would stay at 20 feet above sea level. If we look at this image, you can see the aerial view down in the lower right hand corner. So I have these contour lines that are circular as they go up this island, and in the upper left hand corner you can see this island in elevation profile, and the contour interval, or the elevation change between these lines, is 500 feet. So if I know what the contour interval is and I count these lines, I can figure out what the elevation is at the top of the island. The other thing about contour lines is that the closer the line is to the next line, it indicates a steepness of the feature. And you can see this that on the west side of this island, this is a little more gentle slope than this east side of the island, and the contour lines here are far apart, meaning a gentler slope, and here on the right or on the east side of the island, those contour lines are very steep. So if I were going to plan a hike, I would go up the west side of this island instead of the east side of the island because I'm a lazy hiker. Here's another example of the top drawing shows the elevation contour lines, and the contour interval is 10 probably feet, and then that can be shown or drawn in profile to give you an example or an idea of the steepness. And again, between this edge and here, those lines are pretty far apart, and you can see that that slope is gentler than this slope where the lines are closer together. So those are important clues about contour lines. This is an image from Google Earth, and the contour lines here are a little hard to see, but they have also used what's called shaded relief to kind of let you see that perspective of steepness. And I can see that between here and here, those contour lines are really far apart, and essentially that is a flat plane. And then as I go from here to here, I've got very steep contour lines very close together and a very steep profile. So it's important to know that the contour line is an isoline showing equal elevation. And on a contour map, you have special contour lines that are dark, and those are called index lines. And the index line, I could add this right here if my map were working here. The index line is darker and usually has the elevation value on it, which is really nice and helpful when you're trying to understand where you are on the map. A special kind of contour line that we will look at when we evaluate volcanoes is the depression contour lines. And the depression contour lines are lines that have little hatch marks inside them. And the hatch marks indicate that the land is now going down or decreasing in elevation. So instead of increasing like you would at the peak of a mountain, these are little volcanic vents often, or in when we look at karst landscapes, these are areas where there's depressions or sinks. So the trick about the depression contour is that if I'm starting here at 600 feet in elevation for this first contour line, and my contour interval or CI is 200 feet, as I go up 200, 800 feet, 1,000 feet, 1,200 feet. The next contour line, or the first depression contour, is the same elevation as my last regular contour. So this is kind of showing you the edge, the very edge. It hasn't started going down yet, but it's going to start at this point. And so your first depression and your last regular contour line are the same elevation. And then you can have, on a topographic map, you can have dots and dashes, which are supplemental contour lines. So maybe your contour interval is 20 feet, but as looking at the Willamette Valley, there's some places where there's not a lot of change in elevation, and so they might use what's called a supplemental contour line. So it might be a 10-foot contour. And all of that information would show up here on your map details. So this is an example of the Eugene east topographic map, and you can see that it says the contour interval is 20 feet, and then there are some dotted lines that indicate a 5-foot contour. And so this is Lane Community College in the southern part of the Willamette Valley, and you can easily see the index lines. They're darker brown with the regular contours in between them. And so I want to pull up that map for you, and let's see if I can pull that up here. Maybe or maybe not. Shoot. So I've zoomed into the campus building, and you can see that there is a 500-foot contour line here. This is an index line, and then this is a 600-foot index line. So between the 500-foot and the 600-foot index line, there is 100 feet of elevation gain. And so this is 500 feet. The contour interval is 20 feet. So this next line would be 520, 540, 560, 580, all the way up to 600 feet. So I am in the center building, which is right here, and I have the 500 foot contour line. So this line would be 520 feet. So the center building is at about 520 feet. Now you can see that these contour lines are far apart. So there's a very gentle slope here. These contour lines are closer together. So this would be a steeper slope. And the top of this little hill would be 600 feet plus another 20, 40. So the top of the hill would be 660 feet. So pretty easy once you kind of play around with these different contour options. So I'm looking at a map program called CalTopo, and CalTopo has some really nice options, and we'll be using this off and on this term. But in this example, I have got a topographic map, and I don't know the contour, but it's pretty easy to figure out. So let's see, here is an index line for 2,200 feet. Here's an index line for 2,400 feet. And I have, from this line, it's 1, 2, 3, 4. So there's 5 contour lines. So in 200 feet, that would be 40 foot. So this contour interval is 40 feet. So that way, I would be able, let me see if I can move over here, to identify the elevation of this triangle, which is Luna Butte. If this contour is 200 or 2,000 feet, the next contour is 40 feet, so the elevation of that little triangle would be 2,040 feet. And the elevation of this little stream would be somewhere between 2,000 and 2,040 feet. So I have used CalTopo and zoomed into a section of Florence, Oregon. Let me back up so you can kind of see where we are. So here is the old downtown area of Florence, and I've zoomed in to this area. This is a USGS topographic map, and the contour interval is 20 feet. And so one of the things you might need to evaluate is the impact of sea level rise on existing buildings. And so here is the first 20-foot contour line, and you can see if I go along this line that there are several houses within that elevation difference from 0 at sea level to this first brown line. If you get, say, a 5-foot sea level change and you get a big storm surge, these houses would now be considered in kind of the floodplain. So we're going to be able to use elevation to kind of make predictions and understand what's happening on the surface.